Okay, now for part two, in chemistry of life and water, we'll focus on water. Now, let's pull up our screencast. Let's get going with that. There we go. Water itself is an amazing compound. It is responsible for life on our planet as we know it. Being on an M class planet, we're just the right distance away from our local star for water to be in its liquid form. And if you think about it, life on our planet pretty well has to live between extremes where water can somehow be in its liquid uh, form for survival. Now, you'll find it in its solid state. You'll find it in its solid in its gaseous state. But water's properties are largely determined by its chemical composition. So, few stats here: 60% of your body mass, upwards of 70, depending. It's polar, and that's kind of interesting. I always like to draw this. Let's go back to yellow. Water itself is polar, meaning it's a little bit like a battery, right? With a positive and a negative end. That might be a simplification, but it works out pretty well in the early going. Water is cohesive. Water molecules stick to each other. That's a major reason for water going all the way up from the roots of a plant all the way to the leaves. It kind of helps the water get up there. Stick bugs can float along the surface of water because water molecules, it's almost like a game of Red Rover where they're holding each other's hands. And that creates a certain amount of rope like tension. And that's just enough so that a stick bug can't penetrate through into the water. We call that surface tension. Water can absorb an amazing amount of heat. Whenever you exercise, when you sweat, or if you're ladies, you glow, um, you're the reason your body is releasing water is because it can absorb so much heat. If you want to do something really boring, just sit around and watch water boil. It's amazing how much electrical energy you can put into it on a typical stove, waiting for it to boil. So some pretty neat stuff, and it's due to its chemical characteristics. If you if you haven't seen water before, it's 2 part hydrogen and 1 part oxygen. So let's switch colors a little bit there. I'll just do red there. And it kind of looks like Mickey Mouse, where these are our hydrogens and our oxygen is on the bottom. Now it's interesting, if you notice that, it has a certain angular arrangement. And that angle there, when you look at it, it's fairly broad. And it's like, well, why does it have that angularity? About 107 to 100 and around 110 degrees. Why do hydrogens line up like that? Well, we'll go over that just a moment. Just wait for this, my little friend here, to catch up. There we go. Because, I guess I should accentuate this. There we go. Because of the way that the molecule is aligned, there you go, we refer to it as being a dipole, or having 2 poles. Sort of a positive end and a negative end. And that makes it so that water molecules will interact with each other. Think about it this way. If water molecules begin to hang out with one another, let's go with, I'll just choose a sort of a neutral color here. If you think of the pluses and the minuses as lining up like this, you know which way they'll line up, right? They'll line up in a way where positive charges are lining up with corresponding negative charges. So if we do a little bit of erasing, there we go, that's some quick erasing. When you look at water molecules, what they'll do, give me a nice yellow here, that means the water molecules will always arrange themselves ear to chin. I always describe it that way. They'll always do this. What they won't do, and water doesn't like at all, you won't see this very often. Because the positive charges would be facing each other. So they really dislike that. Okay, that's not what water wants to do. Similarly, I'll just back up a little bit. Water would not like to arrange this way, chin to chin, like this. In fact, the water molecules would rebel. They would totally repel from one another because negative charges would freak out. So they would push away from each other. So undo that just because I need a little more drawing space. And it makes for properties of water. Water is very cohesive as long as it can line up like I've drawn here. And that attraction between the positive and the negative ends, oops, have to choose a darker color here, right? The oxygen is kind of negative and you kind of have a positive. That's a very weak attraction. We call that a hydrogen bond. It's not ionic bonding. No electrons have been donated to make this happen. It just happens that the oxygen end is a little bit negative and the hydrogen end of another molecule nearby, that's a little bit positive. And it's just enough for them to say, oh, I'm kind of attracted to you. Water, being a dipole like this, needs to be explained. Why is it that it lines up in a way where the one end, Mickey's ears at the top, Mickey Mouse's ears, are positive, but the chin is negative? And really, what's the cause of that? Because it makes for some pretty interesting chemistry. Gives water all of its properties. I mean, once water molecules start hanging out together, they're fairly sticky. And because they're attracted to each other, it takes quite a bit of energy to force them apart. They really don't want to fly off as a gas. So it'll take quite a bit to overcome all those little bonds. So we need to explain that now, how this dipole forms. Let's see here. I'm just going to pop down a little bit. Pull out my tray. There we go. And we'll go to this one. That's the one I wanted. Now, there's a trend in the periodic table. When you look at oxygen, oxygen's pretty greedy. Come on. There's a lot of greed with oxygen. And oxygen has a very big nucleus. This is big. It's got 8 protons, for goodness sake. That gives it a lot of pulling power. So if oxygen can swing it, let's see where oxygen is. There we go. Oxygen is just 2 steps away from the end of the periodic table. So again, it wants to be like the nearest noble gas. So if it can just get 2 more electrons, then it would become like neon. It would have 10 electrons in its outer shell. So it's just dying to get there. Now, it either needs a donor or somebody who's going to share. Hydrogen is kind of like the little kid on the block, and not that strong. So unfortunately what happens is oxygen is a bit of a bully. It decides to play with hydrogen, but what it does is it hangs on to electrons. It hoards the toys more than it should. Now, if you've taken chemistry before, you know what I'm doing here. I'm making an analogy for what's called electronegativity. Oxygen, due to its large nucleus, will hold on to the electrons and it won't share with hydrogen proportionally. So what happens with hydrogen is poor old hydrogen only gets to have its electrons part of the time. Just a little bit of lag here. Just a second here. There we go. So hydrogen doesn't get to hang on to its electrons nearly as often. So what that does is it creates kind of an imbalance where the electrons, and I'll just draw, are hanging around, and I'll just draw multiple lines here. They're hanging around on the oxygen end, and oxygen's keeping those toys, those electrons, away from hydrogen because oxygen's nucleus is so big. So hoarding. So this end tends to become more negative. Now, because hydrogen doesn't have its electron nearly as often, well, think about what hydrogen is, right? It's just a proton in the nucleus. So because it's just a proton, it doesn't have the electron to balance that. So this end tends to become net positive. And what we get as a result of that is we get, if I draw the line around it, we get what's called a dipole. And that accounts for water's properties. Now, when you look at water, we'll go back to this slide for a second. I'll give it a second to catch up. Now, the negative oxygen ends are going, the chin, a Mickey Mouse, right, is going to line to the ears of another water molecule. And there will be sort of a weak attraction between positive and negative, and that's a hydrogen bond. Now, it turns out that these bonds are amazing because these kind of bonds, because they're weak, they're sort of like a really weak ionic bond. What they do as hydrogen bonds is they can form and come apart. It's kind of like static attraction, right? Think about a balloon on the wall, right? That's not that hard to pull off. But it's just enough to zip things up. For example, your DNA is sewn up using these bonds. Well, it's good that they're weak so that we can unzip your DNA and read it. And then your DNA can go back together very easily. Turns out to be extremely useful. And hydrogen bonds can form between not just oxygen and hydrogen. You could see this happening between nitrogen and hydrogen. Any element on the periodic table that's fairly electronegative will be holding on to its electrons a little bit more. So, hydrogen bonding, just for the record, is a weak sticky bond. And it's an imbalance in the way electrons are shared, and then it makes molecules kind of have charged regions. Now, it was interesting, the charged regions are sometimes indicated with a partial. So when you go to indicate this, you could say that's the lambda symbol. It just means partially. You'll see this in textbooks sometimes. That's partially positive. This is partially positive. And this end is partially negative, like that. But it's also okay to draw it like that as a dipole, right? It's not, because the lambda means sort of. And that's really what water is. Sort of positive and sort of negative. So your sort of positive will tend to align with your sort of negative. And you sort of get the idea. Pardon the pun. It's just all about the positives and the negatives lining up. When we see those interactions, it explains a lot of things on our planet. Water molecules, for example, can only be pushed so close together. When you look at ice, it's one of the only solids on the planet that's more dense than its liquid. And you say, well, why is that? How can this solid be less dense than what it's floating on? The only reason it floats is because it's less dense, right? That's the whole reason things float. Solid versus the liquid. And I'll tell you the reason for that right now. Water can't be pushed together too much. When you make a solid, you decrease the volume between the particles. Here's the thing. With water, if you try to squeeze it, and you by chance, and it will happen, you try to bring these together too closely, you will get repulsion. And what the repulsion does is it will naturally force the water molecules a little further apart. And you see what's called expansion. And as the water molecules in a solid expand a little bit, their density is the density of solid water is less than the liquid. Water is most dense at 4 degrees Celsius. That's the closest that you can bring water particles together as far as temperature goes. And as you jam them together, they will just naturally repel. And that's why you've probably heard of your pipes bursting in the middle of winter. You want liquid water in your pipes. That takes up a lot less volume. if you take away thermal energy and you force the water molecules together, they will just expand and they'll burst those pipes. So this characteristic of water, where its density is lesser in its solid than liquid form, is a good thing, because can you imagine a local lake, the top layer freezes and then sinks and kills everything as it descends to the bottom? You would have squished fish, mammals wouldn't survive. It'd be terrible. So you can see another reason why water makes life on our planet a possibility. So it's an essential compound. And the neat thing is, because it's charged a little bit, we call it polar covalent, right? Polar, where it has a positive and negative end. Okay, there we go. Well, we call it covalent because it's sharing electrons, right? Remember that hydrogen can be considered a metal and a non-metal? It's really kind of considered as a non-metal when it's combining with oxygen in this way. So it's polar covalent. It has sticky ends. So when you go to wash your hands, it can take almost anything away with it, right? Those little ends will stick to things, little dirt particles on your hands, etc., and just kind of whisk them away. So there's a little bit here about the oxygen being kind of greedy, higher attraction for the electrons, right? And that's the whole basis of electronegativity, where one atom tends to hoard electrons, right? And in this case, it's because oxygen has such a huge nucleus with 8 protons in there. Well, this is just a little bit of the business end of the writing, but makes all these characteristics of water. It makes for its cohesion, where they stick together. Its adhesion, where water, for example, will stick to glass. If you get a glass, just have fun with this. Get yourself a glass of water, and carefully, holding on tight, try to shake the water out of the cup. It won't let go, and that's due to water's sort of polarity and sticking to the glass. So water can absorb a tremendous amount of heat. They call that specific heat. Very exciting. But it's hard to force water molecules apart. It takes a lot of energy to push them apart, too. Those hydrogen bonds are hard to overcome. That's why sweat is such a great thing, right? As we produce water, the water is absorbing our heat and whisking it away. So it's really like a heat sink, if you want to think of it that way. And it helps us to maintain what we call homeostasis, which is our homeo means same, and stasis means, well, means the way we're running. That's a simple definition for you, sort of your status. We want to keep our body temperature around 97 degrees. So releasing water onto the surface of our skin is a great way to be a heat buffer. And because water is polar, you can dissolve so many things in it. And it's pretty neat. I'll just turn off AirPlay for a second here. And I have a little animation for you. There we go. And show you how that works. There we go. So water is a polar compound. Ionic bonding, covalent bonding, we can get rid of that. Here we go. So when you go to dissolve something, so for example, we'll put salt in water. And when you add sodium chloride, it will do what's called ionizing. So we'll do a little close up here. So there's water, and watch the positive and negative ends of water. See how the oxygen go around the positive sodium, and look at how the hydrogen ears go around chlorine like that. There you go. That's called ionizing. So water becomes a very good solvent, and it forms what we call hydration shells, just sort of ring around the rosy with different ions. It's because water has a positive and negative end, so we call that dissolving. True story. One water molecule, an H2O, it's kind of interesting here how they show with the sort of the little curved lines about its sort of charges, and it's attracted to something. Always love the music. There you go. So there's your hydrogen bonds, and you'll see how water will just naturally line up. It's just due to the electric attraction of the ends or the dipole. And there you go, hydrogen bonding. Again, if you want to take a look at those, they're on the course site, videos, etc. All right. So just finish off our lecture here. Pretty well done. A little bit of lag today. Okay. See if that catches up. I think I'm asking my poor computer to do too many things. Water is cohesive, so the water molecules we saw just previously in the animation, they'll stick together. And as I say, that's just enough tension that we call surface tension to keep bugs and some small plants from sinking. So it's due to the hydrogen bonding that things really can't poke through. So that's cohesiveness when water molecules are sticking together. There's not enough cohesion to stop us from going through. We of course weigh way too much. Water molecules are also adhesive; they'll stick to other things. So, for example, water sticking to a glass, water sticking to sugar. You get the idea. And we kind of referred to this a minute ago. Sometimes I do that, but water expands as it freezes because it's less dense. Um, it's less dense in its solid form. Its liquid form is a little, or let me rephrase that. Water is its solid form is less dense than its liquid form. The maximum density of water is 4 degrees Celsius, right? In the fall and in the spring. That's about as close as the water molecules are naturally going to get together. Just the function of temperature to squeeze them together, the water molecules will just repel. So the problem, if you think the last point here where they talk about freezing and the whole issue of frostbite, if water expands in our tissues, then it will destroy the cells. Now we can't humans and many mammals, of course, many animals in the animal kingdom can't be frozen solid because what will happen is the tissues will just burst. Now there are some critters on our planet that make sort of a sugar slush solution in their cells, and water itself will form like a soft sort of snow cone. It won't form those ice daggers that would pierce the cell membrane. That's a little bit different. We don't have a mechanism like that. For example, so we can't be frozen cryogenically as simple. So frostbite is a major problem because it destroys tissues.